Hello, my name is Joe Vasta, and today we will talk about numbers. We'll start with the counting numbers 1, 2, 3, 4, 5, and so on. There's infinitely many counting numbers. Let's put them in a Venn diagram. They're not all going to fit in this picture, so I'll just put 1, 2, and 3. This set of numbers is called the natural numbers. Let's add to our list of numbers. We'll put 0 on the list. We'll extend our Venn diagram to include 0. This bigger set of numbers is called the whole numbers. 3 is a whole number and a natural number. 0 is a whole number but not a natural number. 0 is the only number living in that disk. Let's add more numbers to our list. We'll put negative natural numbers on the list. We'll also extend our Venn diagram to include them. I'll just put -1, -2, and -3 in the diagram. This bigger set of numbers is called the integers. Why don't we add fractions to our list of numbers? We'll extend our Venn diagram to include them. I'll just put 5 fractions in our diagram. This bigger set of numbers is called the rational numbers. A fraction or a rational number is just an integer divided by an integer, provided that you keep it legal. You do not divide by 0. Now you might think 3 isn't a fraction, but all integers can be written as fractions by putting them over 1. Don't you hate when math teachers use these Jedi math tricks? How do you remember natural, whole, integer, rational? Well, no wimps in racquetball. Let's take a look at some of those fractions. 1/2 equals 0.5. 2/3 equals 0.666666, and it keeps going forever. 1/2 is a terminating decimal, whereas 2/3 is a non-terminating decimal. Now 2/3 has a repeating pattern, so it's called a repeating decimal. 9/20 equals 0.45, a terminating decimal. 7/33 equals 0.21212121, etc. It goes forever. It has a repeating pattern. 7/33 is a repeating decimal. Now, -10/7 equals -1.428571, 428,571, etc. It goes forever and has a repeating pattern. -10/7 is a repeating decimal. Any fraction that is written out using decimals is either terminating or repeating. In fact, we could say that rational numbers are terminating decimals or repeating decimals. Now, there's a famous math constant that is related to circles, pi. It goes forever, but it does not have a repeating pattern. It is neither a terminating decimal nor a repeating decimal. It is not a rational number. Pi cannot be written exactly as a fraction, so we need to expand our Venn diagram to include numbers like pi. We put a separate circle that includes non-repeating, non-terminating decimals. Pi lives in that circle. Now, there's a famous math constant that is related to growth, E. E equals 2.71828, 1828. This looks like a repeating decimal. Let's look at more digits. Ah, it fooled us. E is non-repeating and non-terminating. Let's put a few more numbers in that circle. Square root of 2. Square root of 3. Square root of 5. What happened to the square root of 4? That equals 2, which is a natural number. There are other interesting examples. Log 2 or log base 10 of 2. The sine of 10 degrees. And even phi, the golden ratio. The set of all non-repeating, non-terminating decimals is called the irrational numbers. There are infinitely many irrational numbers. If you put the rational numbers and the irrational numbers together, then you get the real numbers. I'm going to tell you what happens in math classes all around the world. They put all the real numbers on a number line. 0 is right in the middle. Here's a surprising idea. Suppose you threw a dart that hit the real number line. What is the probability that the dart hits a rational number? It is 0. There are more irrational numbers than rational numbers. This would imply that there is more than one kind of infinity. The rational numbers are countably infinite, whereas the irrational numbers are uncountably infinite. This is a topic for another time. Let's put all the real numbers into this circle. Are there numbers that contain the real numbers? Let's start by stating a definition. I equals the square root of -1. It's called an imaginary number, but it's as real as the real numbers. There are many real-life applications of imaginary numbers. For example, any oscillation. Now, let's create a new system of numbers by adding real number plus real number times I. We'll extend our Venn diagram to include this number system. I'll use a cloud instead of a circle, and I'll just put 3 of these creatures in our diagram. 3 minus 2i, 1/2 plus root 3i, and e plus pi I. This bigger set of numbers is called the complex numbers. This diagram suggests that any real number is a complex number. We can add 0i to each real number to show that. Now, there are infinitely many complex numbers, and there are perplexing things that I could say about the infinities of real and complex numbers. We can even extend our set of complex numbers to a bigger set of numbers called the quaternions. But I don't want to go there now. So let me leave you with another surprising idea. Consider e raised to the power I times pi. This looks like it will give us a messy number. But no, it gives us -1. This seems unbelievable, but you can prove this if you've taken 1 year of calculus. I hope you enjoyed this video. Have a good day.